Every year, the world melts over 1 billion tons of pig iron. But where does all that fiery metal come from? Imagine a giant furnace as tall as a 35-story skyscraper that never sleeps. Its guts glow like the Earth's core, and the temperature hits 3,600 degrees Fahrenheit. That's 2,000 Celsius. This is a blast furnace. They don't just melt metal here. They give birth to the heart of industry. But there's a secret that only the guys standing at the taphole know. If you stick around to the end, you'll find out what's really happening in the center of this burning fortress, and why it changes everything. Imagine a colossal tower, taller than a 35-story skyscraper. The ground beneath your feet vibrates slightly from its relentless work, and the air is filled with a hum, like the breathing of a giant beast. At night, its top glows, pushing back the darkness. This is a blast furnace, a massive vertical smelter, where 24 hours a day, 7 days a week, the magic of turning ore into metal happens non-stop. Why blast furnace? The name comes from the process itself, and it's no accident. The whole secret to a blast furnace is the constant blast of incredibly hot air that fuels the fire and kicks off all the necessary reactions. If you were to slice a blast furnace open, you'd see it looks like a stretched out bottle. Every part of it has a name and a purpose. The walls of the furnace are lined with special refractory bricks, capable of withstanding temperatures that would melt solid rock. This is a true fortress, built to tame fire itself. So what do they feed into this fiery throat? The process is like cooking from a very strict recipe. The mix of ingredients loaded into the furnace is called the charge. Here are its main components: iron ore, fuel, coke, and fluxes. These three ingredients are loaded into the furnace in precisely measured layers. A layer of coke, then a layer of ore with fluxes, then coke again, and so on. Every few minutes, a new batch weighing tens of tons is sent into the furnace. The iron ore is the foundation of it all. They usually don't just use raw ore dug from the ground, but specially prepared sinter or pellets. These are baked clumps of fine ore, or rolled balls of ore concentrate. The main goal is to have as much iron oxide in the raw material as possible, from which the oxygen will later be ripped out. Coke is coal that's been cooked in special ovens without access to air. After this treatment, it becomes strong, porous, and burns with an immense amount of heat. But that's not its only role. The carbon that makes up coke is the real magician that turns ore into metal. The flux is most often ordinary limestone. Why is it needed? The ore and coke always have useless impurities, so-called gangue. The limestone helps to bind these impurities, forming an easily meltable slag. So, the charge is loaded. What's next? This is where it gets interesting. Two streams move towards each other. From the top, the layers of the charge slowly descend, and from the bottom, a hurricane of superheated gases rushes up to meet them. It all starts at the bottom, in the hearth. Through special pipes called tuyères, air heated to a scorching 2,200 degrees. Fahrenheit, 1 to 200 Celsius, is blasted into the furnace under huge pressure. That's hotter than volcanic lava. Meeting the red-hot coke, the oxygen in the air instantly ignites. The temperature in this zone skyrockets to 3,600 degrees Fahrenheit, 2,000 Celsius. This creates carbon dioxide. But as it rises higher and passes through new layers of coke, it turns into another gas, carbon monoxide. And this gas is the real oxygen thief. As this searing hot stream of gas rises up the furnace shaft, it envelops the chunks of ore and begins to greedily rip the oxygen from them, leaving behind reduced, spongy iron. The reduced iron continues its journey downward into hotter and hotter zones. It passes through the glowing layers of coke and, like a sponge, begins to soak up its carbon. And here's where something amazing happens. Pure iron melts at a very high temperature of 2,800 1,530 Celsius. But soaking up carbon dramatically lowers that melting point. That's why a blast furnace doesn't produce pure iron, but an alloy of iron and carbon, pig iron, which becomes liquid at just 2,200 dodronomers, 1/200 Roughly every 40 to 60 minutes, enough liquid products have collected in the bottom of the furnace. It's time for the climax, a truly mesmerizing sight. A furnace worker, the keeper, uses a special drill to punch open a hole in the furnace wall, the taphole. First, they tap the slag. It's lighter than the iron, so it floats on top. It's a molten, lava-like mass that flows into special ladles. And then they open the iron taphole, and a dazzling, sparking stream of molten metal erupts with a roar. This is the river of fire. The temperature of this stream is around 2,700 degrees Fahrenheit, 1,500 Celsius. It flows down special troughs, bathing everything around in a blinding light, and fills giant ladles that look like railway tankers. Each of these ladles holds hundreds of tons of liquid metal. From here, the pig iron will be sent to its next stage, either poured into molds, or, more often, sent for further processing into steel. A blast furnace is an amazing operation that produces more than just pig iron. The byproducts are just as important. The blast furnace slag, which we've already mentioned, becomes a valuable raw material for making cement, building blocks, and road aggregate after it's cooled and crushed. The blast furnace gas that comes out of the furnace isn't just released into the atmosphere. It's cleaned of dust and used as fuel to heat the very same air that's blasted back into the furnace. It's a closed-loop system that makes the process more economical. Without a doubt, metallurgy is a serious challenge for the environment. However, modern technologies are constantly evolving. When blast furnaces are modernized, powerful filters and cleaning systems are installed to capture dust and harmful gases. Scientists and engineers around the world are working on creating green technologies, like using hydrogen instead of coke, to make metal production cleaner. But for now, the blast furnace remains the king of metallurgy. And every time you see a bridge, a skyscraper, or a train, remember these fiery giants and the people who tame rivers of fire to give the world a strong and reliable foundation. For 75 years, from the late 19th century to the 1970s, the USA was the undisputed world leader in the production of pig iron, steel, and rolled products. During this period, the American iron and steel industry wasn't just a sector of the economy, it was the key, or barometer, of the American economy. In the 1920s, for example, the country produced about half of the world's pig iron. Imagine that. Every other ton of this strategic metal in the world was born right here in American furnaces. Every year, the world produces over 130 million tons of glass. But few people know that behind every clear window, bottle, or skyscraper facade lies a true symphony of fire, air, and light. Imagine a river of molten sand flowing over a mirror of tin, giving birth to perfectly flat sheets of glass so smooth they can reflect the clouds. But there's another kind of glass, one that's alive, with a soul, created by the breath of a craftsman and the fire of a furnace. Stick around to the end, and you'll see how ordinary sand travels through a 3,000-degree journey to become the transparent marvel our world is made of. While the vast majority of architectural glass today is born from a perfectly flat, fiery river flowing over molten tin in the float process, the true soul of the material is revealed in the methods that give it character and uniqueness. This journey from a simple, transparent sheet to a work of decorative art is a fascinating one. To create glass with individuality that carries the mark of a human touch, craftsmen still turn to techniques that have existed for centuries. A glassblower dips his long, hollow pipe into a furnace where a mass of sand and other minerals boils at 2,000 degrees Fahrenheit. He gathers a honey-like ball of glowing glass on the end of the pipe and, skillfully rotating it, begins to blow air into it. The initial bubble, born from his breath, gradually transforms into an elongated, shining hollow cylinder. Thanks to the force of gravity and skillful swinging, this cylinder can reach several feet in length. After the ends of the cylinder are cut off, it's sliced lengthwise and placed back in the furnace. There, under the heat, it slowly unrolls like a scroll, and the craftsmen smooth it into a flat sheet. Glass born this way is never perfectly flat. It's alive, retaining subtle waves, tiny air bubbles, and fine lines that tell the story of its fiery birth. This glass has a watery, organic quality that can't be replicated by a machine. But the creation of unique glass doesn't stop at forming the sheet itself. Other methods transform ordinary sheets into complex decorative elements. Fusing allows artists to literally paint with glass. Different colored pieces of glass are arranged on a base sheet and sent into a kiln, where at 1500 degrees Fahrenheit, they melt together into a single piece, creating bright, painting-like compositions. Closely related is the process of slumping, or bending, where a flat sheet of glass is heated until it becomes soft and sags under its own weight, taking the shape of a ceramic or metal mold placed beneath it. This allows for the creation of curved panels and three-dimensional glass sculptures. Modern technologies add even more possibilities. Lamination allows for baking colored films, fabrics, or even thin sheets of metal between two layers of glass, creating endless variations of color and texture. Sandblasting and chemical etching remove the top layer of glass, making it matte and creating intricate patterns on its surface, from simple geometric shapes to photorealistic images. In this way, by combining ancient crafts with cutting-edge technology, modern production transforms simple glass into an expressive architectural material capable of shaping light, color, and space. In today's world, where tons of used glass containers are collected daily, the journey from the recycling bin to a new bottle isn't just remelting. It's a high-tech odyssey driven by computers and light. Imagine a mountain of crushed glass, dozens of feet high, where clear, green, and brown shards are mixed with labels, caps, and ceramic contaminants. Turning this chaos into pure raw material is a job for a whole complex of smart machines. It all starts with mechanical crushing, where steel hammers turn bottles and jars into fragments a few inches in size. This stream of glass, like a moving river, embarks on a journey through a labyrinth of sorting systems. First, powerful magnetic separators pull out any steel contaminants, and then eddy current systems literally shoot aluminum caps and foil into separate containers. Powerful blasts of air blow away light paper labels and plastic residue. But the hardest task is yet to come. Removing impurities that are almost identical to glass in weight and size, like pieces of ceramic, stone, or porcelain. These enemies of glass don't melt at standard temperatures and turn into defects in new products, so their removal is critically important. This is where optical sorting comes into play. The glass fragments are accelerated on a conveyor belt to high speed and fly through a scanning zone. For a split second, each fragment is illuminated by a bright light, and high-speed cameras take hundreds of pictures. A computer system, with lightning speed, analyzes the images, identifying foreign bodies by their transparency, structure, and shape. As soon as the system spots an opaque piece of ceramic, it instantly calculates its trajectory and commands a battery of air jets. A precise, sniper-like puff of compressed air knocks the unwanted element out of the mainstream, sending it to waste. This process is repeated thousands of times a minute. At the same time, an equally important sorting by color takes place. The same optical systems analyze the spectrum of light passing through each fragment. The machine distinguishes between crystal clear, rich green, and deep brown glass. Depending on the set program, the system can, for example, select only clear glass, knocking out all colored fragments with air jets, or separate the stream into 3 distinct color fractions. The result is a perfectly clean, color-sorted raw material, cullet, ready for a new life without any loss of quality, which is the pinnacle of the modern circular economy. This raw material can then be used to make flat glass. The birth of modern flat glass is a symphony of fire and precision, a spectacular process that turns ordinary raw materials into perfectly transparent sheets. It all begins in a massive melting furnace, the fiery heart of the plant that runs continuously for years. Into this furnace, which resembles a lake of molten fire, a carefully measured mix, or batch, is loaded, consisting of pure quartz sand, soda ash to lower the melting temperature, and limestone for stability. A significant amount of cullet, or crushed recycled glass, is added to this to help speed up the melting process. Inside the furnace, at hellish temperatures approaching 3,000 degrees Fahrenheit, these solid components slowly transform into a uniform, viscous liquid. The melting process is strictly controlled to ensure all particles are completely dissolved and gas bubbles are removed, creating a flawlessly pure melt. From the furnace, this stream of glowing orange molten glass, resembling a river of lava, flows smoothly into a bath of molten tin. This is the culmination of the process known as the float process. The tin bath, stretching for hundreds of feet, has a perfectly smooth, mirror-like surface. Since glass is lighter than tin and doesn't mix with it, it spreads out over the surface, forming a perfectly flat ribbon of uniform thickness. Gravity levels it from the bottom, and surface tension smooths it from the top, creating impeccable optical quality. The speed at which this ribbon is pulled from the bath determines its final thickness with pinpoint accuracy. After forming a perfectly flat surface, the glass ribbon, still very hot but now solid enough to hold its shape, enters the calmest but most critical stage, annealing. It enters a long tunnel known as an annealing layer. If glass is cooled too quickly, its surface will contract faster than its interior, leading to massive internal stresses that will make it brittle and prone to shattering. In the layer, however, the glass temperature is slowly and controllably reduced over several hundred feet, from over 1,000 degrees down to room temperature. This process allows the entire sheet, both surface and core, to cool evenly, relieving all internal stresses. From the other end of the layer emerges a single, flawless, continuous ribbon of perfectly transparent, stress-free glass, ready for automatic cutting into huge sheets that will become the windows, facades, and doors of our world. Imagine this. Every year, the world cranks out over 100 million tons of nuts and bolts, the invisible heroes of our industrial world. They hold together our bridges, our planes, our ships, and even our tallest skyscrapers. But few people know that behind every single one lies a process with precision down to 1,000th of an inch. We're talking metal cleaned in acid, forged under massive presses, hardened at over 2,000 degrees, and tested to its breaking point. So what makes an ordinary bolt strong enough to hold hundreds of tons? Stick around, and you'll learn the secret that turns a simple piece of steel into a part the whole world depends on. A high-volume nut and bolt plant isn't just a factory. It's a high-tech powerhouse where raw steel becomes the hardware that holds our world together. The whole thing is a complex, multi-stage marathon of machining, stamping, heat treating, and non-stop quality control. It all starts with the raw material. High-quality steel wire rod comes in, but it's dirty. First, it needs a serious cleaning to get rid of rust and scale. The most common way to do that? A chemical bath. We're talking a process called acid pickling, where the steel gets a dip in sulfuric or hydrochloric acid. This stuff eats away all the grime, leaving the metal surface perfectly clean and ready for what's next. After the acid bath, the wire is thoroughly rinsed with fresh water to get every last drop of acid off. Then it's dried. For an even deeper clean, some plants use sandblasting or mechanical grinding. You might even see a process called electro-cleaning, which zaps the surface to level it out and boost its rust resistance. On the big production lines, they combine everything: mechanical scrubbing, a chemical dip, a rinse, and a dry. And they don't just eyeball it. Quality control uses visual checks and special instruments to make sure that surface is perfectly clean. Before it moves on, the metal gets a temporary rust preventive coating to keep it pristine during storage and handling. The main ways to make a bolt are cold forming and turning. Cold forming is the real workhorse here. That's where a machine takes the metal wire and shapes it under massive pressure, all without heat. The wire feeds through a series of dies that hammer it into the shape of a bolt. First, the round shank, then the head, usually a hex head so you can get a wrench on it. The beauty of cold forming is that it's incredibly precise, makes the steel stronger, and wastes almost no material. Once the head and body are formed, it's time for the threads. Here, they use a method called thread rolling. Instead of cutting the threads, the bolt blank is forced between special dies that literally press the threads into the metal. This process makes the threads incredibly strong and durable. Some of these high-speed lines can churn out hundreds of bolts a minute. For nuts, they often use hot forging. Steel blanks are heated up to a blistering 2,200 degrees Fahrenheit. That's about 1,200 Celsius, making the metal soft and pliable. Then, a press forges the iconic hex shape. After that, a hole is punched through the middle, and the internal threads are cut on special machines called tappers. Just like bolts, nuts go through heat treatment to make them tough and wear resistant. Heat treating is where a bolt gets its backbone. It's a two-step process, quenching and tempering. First, in quenching, the bolts are heated up and then rapidly cooled. This makes the steel incredibly hard, but also brittle. So the next step is tempering. They're reheated to a lower temperature, which gets rid of the brittleness but keeps all that strength. This is how bolts get their specific grade or property class. After heat treating, every batch goes through brutal quality control. Sample bolts are checked for size, strength, thread accuracy, and any surface defects. We're talking micrometers, go-no-go gauges, and special optical sorters. Any parts that are out of spec are either rejected or sent back for reprocessing. To fight off rust, most bolts and nuts get a protective coating. This could be zinc plating, hot dip galvanizing, or special zinc flake coatings. This is what keeps them from rusting away, especially out in the elements. The finished products are then sorted by size and strength, boxed up, and prepped for shipping. Modern plants have automated lines cranking out hundreds of thousands of these a day. The parts travel on conveyors to automatic sorting machines that use optical sensors to check every last one. Anything that's damaged or not up to snuff gets kicked out. This makes sure only top quality hardware makes it to the packaging line. From there, the nuts and bolts go into automated bagging lines with inline scales and counters that measure out the exact quantity for each package. This could be small plastic bags, cardboard boxes, or bulk bins, depending on what the customer needs. The packages are labeled with all the key info: size, grade, manufacturer, and date. For big industrial orders, they're often packed in bulk bags or large containers to make shipping and storage easier. The whole process is automated to ensure the packaging is sealed tight to keep out moisture, dust, and prevent any damage in transit. Even though most of it is automated, there's still a human touch. For special kits or custom orders, workers will manually check the quality of the packaging, assemble the right mix of nuts and bolts, box them up, and get them ready to ship out. This flexibility allows them to meet specific customer needs with pinpoint accuracy. After packaging, the products go through one last check to make sure the labels are right and the packages are sealed. Then, they're sorted in the warehouse by order and prepped for dispatch. And it's not just standard stuff. Many plants also make custom fasteners based on a customer's specific blueprints, which is crucial for specialized industries like aerospace, automotive, or heavy construction. The global market for fasteners is on a steady climb, and it's all driven by a few key things. First up, construction. As countries spend more on infrastructure, we're talking bridges, roads, and new buildings, the demand for these steel connectors goes through the roof. Second, the automotive and machinery industries. Every car, truck, and piece of factory equipment is held together by hundreds of high-quality fasteners. As those industries grow, so does the need for top-grade nuts and bolts. For example, in Europe, car production is expected to climb, which directly boosts the demand for metal products, including fasteners. At the same time, the steel industry itself is getting smarter, using digital tech and automation to produce better, more specialized products. Of course, the cost of raw materials like iron ore and energy can affect things. But at the end of the day, as long as we're building, driving, and manufacturing, the demand for nuts and bolts isn't going anywhere. Imagine this, a single piece of steel that can hold the weight of 100 fully loaded semi-trucks. How? It's all about a shape engineers call the I-beam. This isn't just metal, it's the backbone of our cities, born from rusted scrap and forged in lightning, fire, and thousands of tons of pressure. But here's the kicker. Why are brand new I-beams almost entirely made of the past? Cars from the 70s, rails from the 30s, even armor from World War II. All of it could be holding up a modern skyscraper. Stick around and you'll learn a secret that will change the way you think about the power of steel. The genius of the I-beam is its shape. The real heavy lifting is carried by the top and bottom parts, so that's where most of the metal is packed, in the flanges. The thin web in the middle just keeps them locked in place. This gives you maximum strength for minimum weight. And that strength is just insane. A single heavy I-beam, set up right, can handle loads of hundreds of thousands, sometimes even millions of pounds. Picture a whole line of fully loaded semi-trucks, all parked on one single piece of steel. That's real power. This story doesn't start in some shiny workshop. It starts in a massive, rusty, noisy yard that looks like a graveyard for metal giants. This is a scrap yard. Mountains of old cars, chopped up rail cars, building frames, and industrial junk are all waiting for a second chance. A giant crane with a powerful electromagnet drops down on the pile, and with a metallic groan, tons of old iron leap up to meet it. This scrap is the main ingredient. It gets loaded into a huge steel basket and sent to the melt shop for its trial by fire. Steel is the undisputed champion of recycling. The recycling rate for structural steel in the US is a whopping 98%. That means nearly every piece of steel from torn down buildings, old bridges, and scrapped ships gets put back to work. On average, a new I-beam made today is 90% recycled metal. This creates an incredible, endless loop. A skyscraper going up today could have a piece of a 70s muscle car, a 1930s railroad track, and even armor from a World War II battleship inside it. This isn't just a hunk of steel. It's concentrated history, melted down and reborn for a new tour of duty. So these numbers aren't just stats. They're the silent language our cities are built on, a language of strength, efficiency, and the almost endless life of metal. Every year, the United States cranks out over 5 million tons of structural steel, and the lion's share of that is I-beams. That's a number so big, it's hard to get your head around. Let's try. The steel in the famous Golden Gate Bridge weighs about 83,000 tons. That means, in 1 year, American mills produce enough beams to build over 60 Golden Gate bridges. The heart of the plant is the electric arc furnace, a giant kettle, the size of a small house, where our scrap metal is dumped with a thunderous crash. 3 massive graphite electrodes, thick as ancient trees, are lowered in from the top. And Then the operator hits the juice. An electric arc, basically a man-made lightning bolt, erupts between the electrode tips and the metal with incredible force. The shop fills with a deep, bone-rattling roar, and the light from the arc is blinding. The temperature inside instantly shoots up to 3,000 degrees Fahrenheit. The metal doesn't stand a chance. It starts to melt, turning into a boiling, blazing lake of steel. Special additives are tossed into this molten bath to get the exact grade of steel needed, strong but flexible enough to handle massive loads. When the steel is ready, it's time to turn this liquid river into something solid. The molten metal is poured into a continuous casting machine. The blazing liquid flows into a special, water-cooled copper mold. As it passes through, the outer layer of steel freezes, forming a thin skin. Next, this still mushy on the inside ingot is continuously pulled downwards through a chamber of water spray where hundreds of nozzles blast it, forcing it to solidify all the way through. What crawls out of the machine is an endless, glowing red, massive steel billet. This is called a bloom. Automated torches hiss to life and slice off pieces to the right length, say 20 or 30 feet. This is our blank, our piece of dough that we're about to shape into a beam. These hot, but now solid blooms are sent to the next furnace, the reheating furnace. It's like a giant tunnel with a fire roaring inside. The blank moves slowly through it, where its temperature is cranked back up to the perfect working heat, around 2,200 degrees Fahrenheit. It becomes soft and pliable, like clay, ready for the most important step, rolling. And this is where the real show begins. The bloom, glowing a brilliant orange, rolls out of the furnace and hits the rolling mill. This is a series of giant steel rollers, like massive rolling pins, lined up one after another. But these rollers aren't flat. They have special grooves cut into them, shaped to gradually form an I-beam. The bloom slams into the first set of rollers. They squeeze it with thousands of tons of force, making it a little thinner and longer. Out the other side, it's grabbed by the next set, which squeezes it from a different angle, starting to form the flanges and the web of the future beam. And so, step by step, passing through dozens of these roller sets, our shapeless billet is stretched and molded, taking on that familiar eye shape right before your eyes. It's an incredible sight. A piece of glowing steel that started at 20 feet long gets stretched into a fiery ribbon hundreds of feet long. The whole mill is filled with a symphony of bangs, screeches, and the hiss of water keeping the rollers cool. When the beam exits the final, finishing roller, it has the perfect shape and dimensions, down to a fraction of an inch. Hot, long, like a fire serpent, it travels down a roller conveyor to a massive cooling bed. This is a giant rack where the beam slowly cools, letting its heat radiate into the air. As it cools, the metal shrinks a bit, and sometimes the beam can get a slight warp. To fix that, after it's cooled down, it's sent to a straightener. This thing is like a giant steel chiropractor, passing the beam through a set of rollers that align it until it's perfectly straight. So, we have a perfectly straight, long beam, but it's not ready to ship yet. Time for the finishing touches. First, it's cut to the specific lengths the customer ordered. This is done by giant saws with blades 6 or 7 feet across. With a deafening scream and a shower of sparks, the saw cuts through the thick steel in seconds. Then, every single beam goes through a tough quality control check. Inspectors measure its geometry, and special ultrasonic machines scan the metal to make sure there are no hidden cracks or flaws inside. Only then does the beam get its marking, its birth certificate, with the steel grade, size, and batch number. The finished inspected beams are picked up by giant cranes and stacked in the yard, or loaded directly onto special railcars or trucks. And just like that, this steel backbone, born from rusty scrap forged through fire and pressure, is ready to ship out to a job site to become the silent but incredibly strong skeleton for a skyscraper that will scrape the clouds, or a bridge that will connect two shores. Standard beams on a construction site can be anywhere from a few inches to 3 feet tall. But then there are the real monsters, the so-called jumbo sections, used in the most critical spots of skyscrapers. Their height can be over 4 feet, and their weight is something else. The heaviest ones can weigh over 800 pounds per foot. Think about that. Every foot of that beam weighs as much as 3 grown men. And a standard length for these things is 60, 80, or even 120 feet. A single one of those beams can weigh as much as a battle tank. Imagine a metal that's lighter than steel, stronger than aluminium, and can withstand temperatures at which other materials simply burn up. A metal used to build aircraft that conquer space and implants that serve people for a lifetime. Sounds like science fiction? But this is titanium, one of the most mysterious metals on Earth. It starts with tiny grains of ilmenite and rutile and ends up as parts for supersonic jets and spacecraft. But few people know. Behind the gleam of titanium lies a manufacturing secret so dangerous and energy intensive that it's rarely spoken of. If you watch till the end, you'll learn something that will forever change your perception of this metal. The story of titanium production begins in the late 18th century when, in 1791, a British clergyman and amateur mineralogist named William Gregor discovered a new metal in the mineral ilmenite, which is now the main source of titanium. Initially, this metal was called menaconite, but later, in 1795, the German chemist Martin Klaproth rediscovered the element in the mineral rutile and named it titanium, in honor of the mythical Titans, giants of ancient Greek mythology. However, the pure metal was first successfully isolated only in 1825 by the Swedish chemist Berzelius, though at that time it was contaminated with impurities and practically unsuitable for industrial use. The first attempts at industrial production of titanium began only in the 20th century. In 1910, the American chemist Matthew Hunter obtained a small amount of pure titanium, and the real breakthrough came in 1925 when Dutch scientists Van Arkel and de Boer developed a method for producing high-purity titanium, paving the way for its widespread application. From the mid-20th century, titanium production developed intensively, especially in the USA, where the metal became indispensable in aviation, the space industry, and military applications. The production of titanium starts with the mining of titanium-bearing raw materials, mainly the minerals ilmenite and rutile, which contain titanium oxides. These ores are found in placer or lode deposits and are widespread across the globe, particularly in Australia, Canada, China, Norway, and South Africa. After mining, the ore undergoes a complex multi-stage processing. First, it is enriched, separating the titanium minerals from the waste rock to obtain ilmenite or rutile concentrates. Then, the concentrates are subjected to chlorination, which results in the formation of titanium tetrachloride, a volatile substance that is purified by distillation. This process allows for the removal of impurities and the production of a high-purity intermediate product. Next, the titanium tetrachloride is reduced with magnesium or sodium in special reactors at high temperatures in an inert atmosphere, producing titanium sponge, a porous metallic powder. This titanium sponge is then pressed, melted, and cast to obtain ingots or billets for further processing. The production of titanium is energy-intensive and expensive due to the complexity of the technological processes and the need to work in high-purity conditions. The main industrial method for producing titanium is the Kroll process, which remains the global standard. It involves the chlorination of titanium ore, purification of titanium tetrachloride, and its reduction with a metal, allowing for the production of high-quality metal for aviation, space technology, medicine, and other industries. Thus, titanium production begins with the mining of ilmenite and rutile, goes through complex chemical reactions and physical processing to transform natural minerals into a high-tech metal that combines lightness, strength, and corrosion resistance. The initial stages of titanium production are based on a complex, multi-step technological process that begins with the extraction and preparation of titanium-bearing raw materials, mainly ilmenite and rutile. These minerals contain titanium oxides, which must be converted into chemically pure titanium tetrachloride. To do this, the titanium ore concentrates are chlorinated in fluidized bed reactors at a temperature of 1,800 degrees Fahrenheit, where carbon and chlorine gas react with the raw material to form titanium and carbon monoxide. This tetrachloride contains impurities of other metals, which are removed by distillation to obtain high-purity technical titanium. The next key stage is the reduction of titanium tetrachloride to metallic titanium. The most common industrial method is the Kroll process, in which titanium tetrachloride reacts with magnesium in a vacuum chamber at high temperature. The result is titanium sponge, a porous metallic powder containing impurities of magnesium and magnesium chlorides. This reaction mass is subjected to vacuum distillation to remove impurities, after which the titanium sponge is pressed and remelted into solid ingots or slabs. The resulting titanium ingots are then used to produce alloys, rolled products, sheets, and complex parts. The entire process requires strict control of purity, temperature regimes, and safety, as titanium actively reacts with oxygen and nitrogen when heated. Just look at how incredible it is. A porous, light, and seemingly fluffy mass of metal. This is titanium sponge. It looks nothing like a regular metal bar, but more like a piece of metallic sponge or foam, only made of titanium. But this fluffy material is the first step towards creating strong and reliable titanium ingots, which are then used in aviation, medicine, and other high-tech industries. First and foremost, titanium ingots can be used to create titanium alloys, mixtures of titanium with other metals that enhance its properties. To obtain an alloy, alloying elements are added to the molten titanium, most often aluminium, vanadium, molybdenum, iron, or niobium. These additives change the metal's structure, increasing its strength, heat resistance, corrosion resistance, and improving its workability. The production of alloys usually takes place in vacuum arc furnaces, where the metal is melted at high temperatures in a protective atmosphere to avoid oxidation. To achieve a homogeneous composition, the alloy is remelted several times, after which it is cooled and prepared for further processing. The next stage is rolling. Ingots or slabs of titanium and titanium alloys are heated to a certain temperature to make the metal more malleable and are passed through special rollers. Rolling allows for reducing the metal's thickness, giving it the desired shape and size, as well as improving its structure and mechanical properties. The result is various types of rolled products: strips, ribbons, wire, and bars. Rolling can be hot or cold, depending on the requirements for the final product. From these rolled products, sheet metal is made, thin, flat blanks that are widely used in construction, aviation, medicine, and other industries. Titanium sheets are distinguished by their high strength and corrosion resistance, and are also easily subjected to further processing, cutting, bending, and stamping. The production of sheets requires precise control of thickness and surface quality, so after rolling, they are often subjected to additional processing, such as polishing or anodizing. To create complex parts, various methods of processing titanium and its alloys are used. These can include mechanical milling, turning, grinding, as well as modern technologies such as additive manufacturing using laser powder bed fusion. Additive technologies allow for the creation of parts with complex geometries that are impossible to produce with traditional methods. This is especially important for the aviation and medical industries, where lightweight, strong, and precise components are required. Furthermore, to enhance their performance characteristics, titanium products can undergo heat treatment, annealing, quenching, or aging. These processes change the internal structure of the metal, improving its strength, hardness, and fatigue resistance. In aviation, titanium is used for 15% of the weight of a modern passenger aircraft, significantly reducing its overall weight and increasing fuel efficiency. In the medical field, about 70% of implants, such as artificial joints and dental prostheses, are made from titanium or its alloys due to their biocompatibility and durability. Every year, over 4 billion miles of fiber optic cables are produced worldwide. That's enough to wrap around the Earth more than 160 times. But few people know that their journey begins with sand. A special kind, whose purity is measured in parts per million. Because even one microcrack can destroy a signal that's racing for thousands of miles at the speed of light. What is this magic? How does ordinary sand turn into transparent threads, thinner than a hair, but stronger than steel? Watch closely. At the end of this video, you'll learn a secret you've never heard before. To create a thread capable of transmitting light at a speed of over 186,000 miles per second, you have to start with sand. But not just any sand, only special, extremely pure quartz sand, where the main substance is silicon dioxide. For fiber optic production, sand with a silica content of over 99.9% is used, which means in 1 million parts, there's only 1 part of impurities. Imagine this. In every pound of raw material, no more than a few millionths of an ounce of impurities. And this is critical, because even 1 billionth of an inch of foreign metal or organic matter can cause light scattering or absorption in the fiber optic cable. And then the signal, which was supposed to travel 60 miles without amplification, simply disappears. Raw material for fiber optic cable isn't just washed or filtered, it's purified at the molecular level. Manufacturers often use vapor phase chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and deposited as pure vapor. And only then is it converted back into glass. Add to this strict control of temperature, humidity, and air currents in clean rooms, and you'll get an idea of how far this is from an ordinary sandy beach. Production laboratories look more like National Aeronautics and Space Administration sterile zones than a glass workshop, and all for the sake of ensuring there's not a single defect in every yard of the future fiber. Because when you're transmitting light over thousands of miles, even one microscratch can cost you signal quality. A large, transparent glass cylinder that will later be melted and drawn into a very thin thread. This is the fiber optic preform. This huge glass rod is made using a method called vapor deposition. In a large furnace, air is mixed with very pure gases. These are different substances that turn into vapor when heated. These vapors hit the inner surface of a transparent tube, which is heated very intensely. When the vapors touch the hot wall of the tube, they deposit and turn into tiny droplets of glass, like dew collecting on leaves in the morning. Gradually, these droplets collect, layer by layer, until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it collapses into a dense solid rod, and this is our preform. The preform is placed in a special furnace that heats up very intensely. The temperature inside it reaches approximately 4,700 degrees Fahrenheit. This temperature is so high that the glass becomes soft and starts to melt, like caramel on a stove. When the end of the preform melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and a thin thread is formed from it. This thread, the optical fiber, is drawn at a speed of approximately 1,000 feet per minute. Imagine that. It's faster than a cyclist moving through the city. It's important for the thread to be of uniform thickness throughout its length. The thickness of an optical fiber is usually around 125 microns, or approximately 0.005 inches. That's very, very thin. For comparison, the average human hair is about 100 microns thick or less. To keep this diameter under control, special instruments are used during the process. They look at the thread in real time and measure its thickness. If the thread starts to become thicker or thinner, the system automatically changes the drawing speed or the furnace temperature to correct it. After the optical fiber has been drawn from the preform and has become a thin, transparent thread, it needs to be protected. The fiber is very thin and fragile. If left unprotected, it can easily break. Cracks will appear, or dirt will get on it. Therefore, immediately after drawing, the fiber is coated with a special protective layer. A thin thread is pulled from the furnace. After the furnace, the thread immediately goes into a coating machine. This is a special device that clothes the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. It's like a small tube, or nozzle, inside which there's molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly applied to it. The polymer has very low viscosity, so that the coating is thin and even, but dense enough to protect the fiber. This coating layer usually consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks and allows the fiber to bend. The secondary coating is harder and more rigid, protecting against external influences, dust, and scratches. These two layers are applied sequentially, one after the other, to provide reliable protection. After applying the liquid coating, the coated fiber passes through special forming rollers. They regulate the thickness and evenness of the layer, pressing the coating uniformly along the entire length of the fiber. These rollers are very precisely calibrated so that the layer is not too thick or thin. After the polymer has been applied and shaped, the fiber passes through a zone of ultraviolet light. Here, the polymer instantly hardens under the influence of ultraviolet lamps. This is a process called polymerization. Anyone who gets their nails done knows how this happens. Ultraviolet lamps emit light of a specific wavelength that activates chemical reactions in the polymer. Thanks to this, the coating quickly becomes solid, while retaining its elasticity and ability to protect the fiber. This is a very fast process. The coating solidifies in fractions of a second, literally. This method does not heat the fiber, so it doesn't damage it. This provides very strong and durable protection. The entire machine is equipped with sensors and control systems. They constantly measure the coating thickness, fiber feed speed, and uniformity of application. If the coating layer is too thin, or there are defects, the system either stops the process or adjusts the parameters to avoid defects. At the end of all this technological magic, a spooling module, rotating with a hum resembling the sound of a jet engine, only in miniature. The fiber, like transparent silk, lies down smoothly and precisely, coil after coil. It shimmers in the light of the lamps, reflecting cold blue and white hues. The spool moves smoothly, to the left, then to the right, with millimeter precision, as if an artist is painting pictures with movement. One wrong angle, and everything will go haywire, so the system automatically adjusts the rotation speed and fiber tension with surgical precision. Around are sensors, lasers, cameras. They carefully ensure that the fiber lies flat, doesn't twist, and doesn't create tension. With every minute, more and more layers appear on the spool. Imagine, in a few hours, there are already several feet of thin, almost invisible fiber there. And all this without a single break, without a single scratch. Because even a micro crack and the light signal will get messed up, like a radio wave in a storm. Before cable assembly begins, the fiber from the spool is carefully wound onto a production line. Since one cable usually contains several fibers, individual threads are combined into ribbons or modules. For ribbons, the fibers are arranged parallel in a single plane, for example, 12 pieces, and glued together with a special resin. This makes them easier to work with during connection. For bundles, the fibers are twisted into a spiral strand and placed in a plastic tube. These ribbons or bundles are then placed into buffer tubes, thin, flexible plastic channels that provide space for the fiber's slight movements. This is important because when the cable's temperature changes or it's bent, the fiber slightly expands or contracts, and the buffer tube helps prevent it from being damaged. A gel that repels water and absorbs vibrations can also be added inside these tubes. Around the buffer tubes, strengthening elements are added. Fiberglass or Kevlar, very strong threads that protect the cable from stretching. Metal wire, for additional mechanical strength or grounding. A central strength member, a rigid element in the center that maintains the cable's shape. These reinforcements are needed so the cable can withstand tension, impacts, bending, and remain intact for decades. All of this is wrapped in an outer jacket. This is a dense plastic or polyethylene pipe, resistant to ultraviolet light, moisture, rodents, and temperature fluctuations. The cable is tested. The bandwidth of each fiber is checked, as is its bending strength and resistance to moisture. Then it's wound onto large drums, marked, and technical documents are added, and it's ready for transportation and installation. Every year, billions of square feet of concrete are born in the world, but only a few know about the material that has turned construction on its head. Imagine this. In a single shift, one machine can create almost half a mile of slabs, and the annual output in North America is over 200 million square feet. That's the area of 30 pentagons. How do these lightweight slabs, weighing thousands of tons less, support entire buildings? The secret is hidden in their steel muscles and the mysterious voids inside. Watch till the end, and you'll discover something most people don't even have a clue about. The slip former machine crawls along a 600-foot casting bed at a speed of about 4 feet per minute. Doesn't sound too quick? Well, let's do the maths. That's 200 feet an hour. That's almost the length of an Olympic swimming pool, born from concrete in less than an hour. In a single 10-hour shift, one of these beds can churn out nearly half a mile of perfectly formed concrete slab. And a big plant might have several of these beds. This isn't just building, it's a conveyor belt running at a speed unthinkable for traditional pour-on-site concrete. And now for the main trick, the hollow cores. These holes inside aren't just for looks. They slash the slab's weight by almost 50% compared to a solid slab of the same thickness and strength. What's the payoff? Picture this. You're building a 100,000 square foot office block. If the floors were made from standard, solid concrete, they'd weigh about 5,000 tons. But with hollow core slabs, just 3,000 tons. We've just stripped 2,000 tons of dead weight from the building. That's the weight of about 500 adult elephants that the foundations, columns, and beams no longer have to carry. This allows the entire structure to be lighter, more slender, and most importantly, a whole lot cheaper. But how can such a light slab be so strong? The secret is in those tensioned steel muscles. The concrete used in these slabs isn't what you'd find on the footpath. It's high-strength concrete that can handle pressures over 8,000 pounds per square inch, while standard concrete manages only 3,000 or 4,000. and the steel strands inside are tensioned with such force that they create a constant state of compression within the slab. Because of this, a hollow core slab can easily span 60 feet with no intermediate support at all. 60 feet. That's the width of a professional basketball court. Imagine a huge open space with not a single column in sight. That's exactly why these slabs are a favorite for building car parks, supermarkets, and open-plan offices. Every year, over 200 million square feet of hollow core slabs are produced in North America. The number is just staggering. It's enough area to build 30 colossal buildings like the Pentagon. Every single year. This isn't just a building material. It's an entire industry built on speed, efficiency, and clever use of resources. So these figures aren't just dry data. They're proof that sometimes, to get stronger, you just have to get rid of the unnecessary stuff on the inside. It all starts not in a concrete mixer, but on a massive, perfectly flat runway inside the workshop. This is the casting bed. Imagine a perfectly smooth, polished steel track a few feet wide, but 600 feet long. That's longer than 2 footy fields, end to end. Beneath this track run pipes circulating hot water or steam to keep it warm. This is the perfect cradle for the birth of our future giant. At both ends of this track stand massive steel abutments, anchored into a thick concrete foundation. They're like steel teeth sunk into the earth, and their job is to withstand simply inhuman loads. Between these two abutments, high-strength steel strands are stretched. This isn't your average wire. It's several steel filaments twisted together, each capable of holding the weight of a car. They are laid out along the entire 600-foot length of the bed, forming the slab's future skeleton. One end of each strand is securely fixed in an abutment. The other is hooked up to a giant hydraulic jack, and this jack starts to pull. It tensions each of these steel strands with a force of 30 or 40,000 pounds. That's like hanging 3 full-sized utes off each thin strand. The steel muscles tense up, becoming as taut as the strings of a giant guitar, storing a colossal amount of energy. This is secret number 1, pre-stressing. When the steel skeleton is strained and singing with tension, the star of the show appears, the slip former. This is one of the most incredible machines in the construction world. Imagine a strange, low-slung, self-propelled creature, slowly crawling on rails along our long bed. It has a large hopper on top, which is filled with concrete. But this isn't your typical liquid concrete. It's what's known as zero-slump concrete. It's so dry it looks like damp earth. If you picked it up, it wouldn't flow through your fingers. And so, this machine begins its slow journey. Inside, a real marvel takes place. Firstly, the concrete from the hopper is fed downwards, enveloping our tensioned steel strands. Secondly, special vibrators and compactors ram this dry mix with incredible force, making it unbelievably dense. And thirdly, and most importantly, inside the machine are special forming tubes, or mandrels, which vibrate as they push through the concrete, leaving behind perfectly round, smooth voids. The machine, like a giant concrete snail, slowly crawls forward, leaving in its wake a perfectly formed, endless concrete slab, with hollow cores inside and tensioned steel muscles hidden within its body. Because the concrete is so dry, it holds its shape instantly and doesn't sag. This is secret number 2. The voids, which make the slab 50% lighter than a solid one while barely reducing its strength, as the top and bottom sections do most of the work. Once the machine crawls to the end of the 600-foot bed, its job is done. But our slab is still green and weak. It's time for a spa treatment. Workers cover the entire length of this concrete ribbon with huge insulating tarps, like blankets. Hot steam is then pumped under these blankets. This creates a sauna effect, which dramatically speeds up the chemical reaction of the concrete curing. Under normal conditions, concrete needs weeks to reach its full strength. But in this hot, humid atmosphere, it achieves the required strength of over 5,000 pounds per square inch in just 12 to 24 hours. When the concrete has set and become hard as rock, it's time for the release. Workers slowly let off the pressure on the hydraulic jacks. The tensioned steel strands, now permanently bonded to the concrete, try to shrink back to their original length. But the concrete won't let them. As a result, this massive compressive force is transferred to the concrete slab itself. Now it's not just a concrete slab, it's pre-stressed or compressed. This means that when a load from above tries to bend it, it first has to overcome this built-in compressive force. This is what allows it to span huge distances without extra support. And the final act of this performance, the cutting. A giant saw travels on rails along our long concrete ribbon. It's a monster with a massive blade coated in industrial diamonds. With a deafening roar and a spray of sparks and cooling water, this saw cuts the slab with incredible precision into sections of the required length, according to the order. The finished, perfectly flat, lightweight, and incredibly strong slabs are then picked up by giant cranes and loaded onto trucks. And just like that, after a journey from a tensioned steel string to the slow crawl of a concrete snail and a final diamond cut, this brilliant piece of engineering is born, ready to become the fast, efficient, and reliable flooring in the buildings where we live, work, and play.